Okay, so we were in the middle of talking about adjunction and inversion of adjunction. Maybe I should say a word on terminology. So usually people say it's adjunction when you go from X to the divisor S, and people say it's inversion of adjunction when you want to make a statement that something on S implies something on X. But we're kind of talking about both directions right now. So recall we were in the situation where X comma S plus delta is a log pair with S normal integral phase divisor and then we showed that and we also want to assume that the S and the delta don't share any components. So then we showed that there was a unique divisor the different with a bunch of properties, but namely that with the different, then adjunction holds as you might expect. So it's basically the correction term to adjunction. Two, we can compute it by taking a log resolution. So if we take a log resolution where we assume that the push forward of sy is s, the push forward of delta y is delta, and that it's crepant. So maybe I never formally defined this, but sometimes people call log resolution satisfying all these conditions, and that the pullback of kx plus s plus delta is ky plus sy plus delta y. Sometimes people say these are crepant because there are no extra discrepancies. Kind of you put all the discrepancies into the boundary. And in the case where the boundaries are empty, then there are just no discrepancies at all if this is satisfied. Anyway, so if you take a crepant log resolution, then we said that you can compute the different by first computing the different upstairs. And in that case, it's just delta y restricted to sy, and then pushing forward. And that with this condition, we also see that the pullback of ks plus the different along the restriction of f to s is ksy plus delta y restricted to sy. And so in particular, this pair sy with its different is also a crepant resolution, a crepant log resolution of s with its different. So everything we want to compute, we can compute with a log resolution as long as we pick this delta y. And then from part 2, we see that actually if delta is effective, which is really the case we care about, then the different is effective, which is definitely not clear from the definition in terms of the dualizing sheaf or the canonical sheaf. But it is clear from this definition because delta y is effective, so and also shares no components with sy. So when we restrict, we get something effective. And then the last part is that you can generalize to the case where s is not normal by taking the normalization and then it's essentially the same thing, except now you have to be careful about the fact that normalization. You have to be careful about the fact that under normalization, the canonical changes. So we also need to correct by the relative canonical of the normalization. So as an example here, and this won't, so in a second, we're going to prove some properties that show that for the cases we care about, like studying DLT pairs using using induction and restricting to these divisors with coefficient 1, in that case, actually, all our divisors will be normal. So for MMP purposes, you don't really care about the non-normal situation. But this non-normal situation does come up when you're studying, for example, log canonical pairs. Then you really have these non-normal log canonical centers. And also it comes up in moduli theory, which I'll say a few words about next week. But okay, so we want to correct, and here's the basic example of this. If we have just a node in P2 with coefficient 1, then and this is S, and we have no delta, then the normalization is a P1. How does the canonical pull back under the normalization? Well, the canonical of the node is trivial. The canonical of P1 is O of minus 2. So the correction term, this relative canonical, is 2 points. And what are those 2 points? They're exactly the preimages of the node. And so in this case, I called it new, I guess. So in this case, new upper star of KP2 plus S is K of the normalization plus those 2 points. And so the different is those 2 points that lie over the node. And so in general, you basically have the same definition with the same properties where you have this component coming from delta y, but then you also have to add in, you have this component coming from delta, and then you also have to add in the relative. But the point is that actually in this log resolution point of view, SY is going to be normal because we've taken log resolution. So definition 2 kind of already works in the non-normal case. Okay. So let's give some properties. Well, no, not properties. Some propositions that are useful for working with DLT pairs using induction and using adjunction. So basically, proposition that says that for DLT pairs, we can pick out these normal components S that we can then restrict to and try to apply induction. So let X comma delta be a DLT pair. Then the following are equivalent. 1, the pair is PLT. So recall this means that the discrepancies are strictly bigger than -1, but no assumption about the round down of delta. So delta can still have coefficients 1, but the discrepancies are bigger than -1. 2, the round down of delta is normal. And so the components of the round down will form our various S divisors that we're going to apply adjunction to. And the point here is that the round down might not be irreducible. There might be multiple components with coefficient 1, but if you're PLT, they have to all be disjoint. They can't intersect. And 3, the round down of delta is a disjoint union of its components. Of the irreducible components. So again, basically the components in the round down don't intersect each other. So 2 and 3, those I won't say I won't like write down the proof, but 2 and 3 basically come from the computation of discrepancies when you have 2 divisors with coefficient 1 that intersect. So anytime they intersect, if they have coefficient 1, well, you reduce to the case of surfaces, and then you have two curves with coefficient 1 intersecting, and then there you'll get a discrepancy that's exactly -1 if they're intersecting nodally. And so 2 and 3, the fact that the round down has to be normal, or the fact that the components can't intersect at least comes from the fact that that the discrepancies have to be strictly bigger than -1 for PLT pairs. So the interesting part is that this PLT implies that this round down is actually normal. But yeah, maybe I butchered that. So okay, let me just write down the exact statement. Okay, so we'll do 1 implies 2. So take a log resolution. And write down ky plus delta y is equal to the pullback of kx plus delta plus some a, where delta y in this case is the strict transform of delta. And now by the PLT assumption, this a has coefficients that are strictly bigger than -1. So the roundup of a, let's call it e, is effective and f exceptional. So this is by PLT assumption. Okay, so then let's look at S, the round down of delta. So this is the thing we want to show as normal. Well, there's an SY, which is the round down of delta y, lying over S, and we have that the push forward of SY is S, just because delta y is a strict transform. So the coefficients stay the same. So the components of coefficient 1 in delta are the same as the components with coefficient 1 in delta y. And now we're going to write down a sequence for restricting to S. This effective exceptional piece. Okay, and now the observation is just from this formula here. If we rearrange and take some roundups, and we're going to ignore the pullback from the base part. We're going to ignore this f upper star kx plus delta. So we're just going to work with f linear equivalence or f numerical equivalence. But if you just mess around with that equality, then we'll get that minus sy plus e. Well, by definition, this is minus the round down of delta y plus the round up of a. Those are the definitions of E and SY. And now this is F numerically equivalent to KY plus the fractional part of delta plus the roundup of E minus the roundup of A, I mean. E is already the roundup. The roundup of A minus A. Okay, so all I did was put numerical equivalence, so we'll ignore the pullback and then rearrange the boxed equation. But now the point is that this fractional part of delta y, that's some effective divisor with coefficients strictly smaller than 1 because the fractional part. The roundup of a minus a also has coefficients strictly smaller than 1, and it's effective because the roundup of a is effective. And a has coefficients all strictly bigger than -1. And so what we get here is that y with this delta y with this fractional part plus the roundup minus a is KLT. Because we have this normal crossings divisor with coefficients all strictly smaller than, that's effective, and with coefficients strictly smaller than 1. And so we have that the thing, this first line bundle, this OI of minus SY plus E, is numerically equivalent to the log canonical for a KLT pair. And so by Grauert, Riemann, Schneider vanishing, since y is smooth, we know that R1 F lower star of OY minus SY plus E is 0. So Grauert, Riemann, Schneider vanishing said if you had a smooth guy and a projective morphism and a KLT pair, then if you have a divisor that's numerically equivalent to your log canonical divisor plus an F divisor, then you have this vanishing. Here, our F divisor is just 0 because our divisor is just already equivalent to the log canonical divisor for this KLT pair. So that's 0. So that tells us that the push forward is surjective. This restriction map on push forwards. But now E is effective exceptional. So this is just OX. On the other hand, if we write down the composition, we have OX surjects onto OS. That's the structure map. That's compatible with the isomorphism of F lower star OY of E with OX. And now we have the composition with F lower star OSY. And then this includes into F lower star OSY twisted by E because E is effective and push forward is exact on the left. So we have this, and then this map is this composition, which we just showed is surjective. So that implies that the map OS to F lower star OSY is surjective. But this factors through the normalization because SY is smooth. So SY is some smooth dominant birational guy that maps down to S. So F lower star OSY, like the natural map OS to F lower star OSY factors through the normalization. Because it's surjective, that means it has to actually be the normalization. So. And so we've shown that S is normal. Okay. So that, yeah, right. So that then what are the other pieces of the proposition? So, okay, the components being normal imply 3 by this computation of discrepancies. Sorry, the components being normal imply 3 just by definition of normality. 3 implies 1 by the computation of discrepancies. Okay. Any questions about that? Okay, well, and the important point then is that we have this corollary that lets us perturb DLT pairs to something where we just have a single normal irreducible divisor that then we can apply adjunction and then induct to prove things about the minimal model program. So suppose x comma delta is DLT and let S be some component of the round down. And then let's write delta as S plus delta 1. So just put everything else inside of delta 1. Then S is normal. So basically every component with coefficient 1 for a DLT pair is actually normal. So proof with the notation that I already set up. I guess this notation is really part of the proof, but I already wrote it down. So with this notation, let's consider the following. So basically what we want to do is we want to write down S plus 1 minus epsilon delta 1. And why do we want to do that? Well, we want a pair that's DLT and whose round down is just S. If we know that the round down is just S, well, S is irreducible, so then we can apply the previous theorem, and we know that condition 3 is satisfied, because if the round down is just a single irreducible component, then it's a disjoint union of its components. And therefore, x comma delta is actually PLT, and this round down S is normal. So basically what we want to do is just make this perturbation and say that this perturbation is DLT. And then we're done. The issue is that this delta 1 is not necessarily Q Cartier. And so we can't really do this perturbation, because then we don't have a log pair. If we subtract some non-Q Cartier divisor, then our log canonical is no longer Q Cartier. And so we have to be a little more careful with this perturbation. Basically what you do is you add, you subtract delta 1 and then add back some generic ample plus delta 1. And so the lemma is that there exists, and this is 2.43 in Kolar-Mori. I'm not going to write down the proof, but basically there exists a D that's equivalent to epsilon delta 1 plus some large enough ample, such that if we add epsilon D, then this pair is DLT. So basically we kind of move around epsilon delta 1 using an ample, and now because we've added back this, like this pair is Q Cartier because it's equivalent to S plus delta 1 plus epsilon of our ample. So we're adding an ample, everything's Q Cartier. But we've perturbed it a little bit so that we've kind of moved some of the delta 1 piece into the D, and now everything has small coefficient because this D has coefficient epsilon. So now this thing is DLT, but it's round down but the round down is just the single component S, and so S is normal by the previous proposition. Okay, so this is how we perturb DLT pairs to kind of pick out a single irreducible normal divisor that we then want to apply adjunction to. And now, finally, we have the comparison of discrepancies. So this is maybe sometimes called adjunction. So I'll write down a pair x comma s plus delta. S integral and normal. Then for every divisor ES lying over S, there exists a divisor E lying over X such that the discrepancy of ES for the pair S comma the different is equal to the discrepancy of E for the pair X comma S plus delta. And this implies that we have the following inequalities: the total discrepancy of our pair S comma the different is greater than or equal to the discrepancy running over all divisors with center contained in S. So if you recall, the discrepancy was this infimum over the discrepancies of all divisors that are exceptional. And here we're just going to take all divisors that are exceptional and whose image lies inside of S for the pair X S plus delta. And then this is greater than or equal to the discrepancy over all divisors whose center intersects S. So maybe it doesn't lie inside of S, but now we look at more divisors where the center intersects. Okay, so then we have these sequence of inequalities, and this tells us something about the singularities of S comma the different. Okay, so any questions about that statement? So let's write down our Krepin log resolution. Then we know that the pullback of Ks plus the different is equal to Ksy plus delta y restricted to Sy. And let's assume further that we've blown up so that we've separated S from all the components of delta. So in this case, then every divisor that has a non-zero discrepancy with center intersecting S. So every divisor we're looking at in these inequalities, it's either exceptional for Y, or it's one of the divisors of delta Y that intersect Sy. But because we've blown up further, all the divisors of delta Y that intersect Sy are exceptional. So actually, all the divisors that we're dealing with in these inequalities of discrepancies are F exceptional. So. But note that just because they're F exceptional doesn't mean that they're exceptional on S, because we could have a divisor that's contracted to something in X, but that the thing that's contracted to is still a divisor inside of S. So for example, if we have a divisor on Y that gets contracted to something codimension 2 contained in S, well, if it's codimension 2 in X, then it's codimension 1 in S. So all these divisors are F exceptional, but they're not exceptionals for S itself. And so that's why in these inequalities, we have the total discrepancy on S, because we need to consider divisors that are not necessarily exceptional, is greater than or equal to the regular discrepancy on X, because we've blown up, so we've separated out all of the non-exceptional divisors and are now only looking at exceptionals. Okay, and now we want to do some further blowups to make sure that we see any divisor ES. So the first part was that for any divisor ES on S, we can actually compute the discrepancy, like there exists a divisor on X with the same discrepancy. And basically how we do that is we say, so there was this lemma previously that said we can take a sequence of blowups of S such that ES appears on one of these blowups as a divisor. And so if we want to produce E, we just blow up the same subvarieties, the same sequence of subvarieties of S, but we blow them up inside of all of X. So this will give us a divisor. So if we assume that Y dominates these blowups, so assume that we've done these blowups and then resolved further to get all the other conditions, then this gives us a divisor E in Y such that the intersection of E with SY is equal to a divisor ESY with center with center on SY of E equaling ESY. So basically, we get it by doing these blowups all inside of X itself. Then we get a divisor whose intersection gives us a model for a divisor ES. And so now it's just a matter of computing the discrepancies. So on this log resolution, we see all the divisors. So the discrepancies are just minus the coefficients of the boundary. But then by adjunction, we know that discrepancy equals minus coefficient for a divisor appearing on Y. And so now we just write down, well, KY plus SY plus delta Y restricted to SY is KSY plus delta Y restricted to SY. And so the coefficients are the same. So we have a component E inside of delta Y. It comes with some coefficient, which is minus its discrepancy. When we restrict, we get exactly the component ESY inside of this restriction that has the same coefficient, so it has the same discrepancy. So that proves the equality of discrepancies, and then just the fact that we've produced this resolution and we see all the discrepancies for Y, if we see all the discrepancies on S, gives these inequalities, because now we've shown that every divisor can appear on some. Every divisor on S can appear as the intersection of some divisor on some resolution, and we have the inequalities for this particular resolution. So we're done. Okay. So the point is that this gives us the easy but useful version of adjunction. So sometimes it's called easy adjunction. It's easy in the sense that the other direction's very hard. So in the same situation, if S plus delta is PLT, then S comma the different is KLT, and 2, if X comma S plus delta is log canonical, then S comma the different is log canonical. Okay, and so the proof of this is just apply what we just said above. So the discrepancies of S are bounded below by the discrepancies of the divisors on X that happen to intersect S. And so if all the divisors on X have discrepancies bounded below by -1, then all the divisors over S have discrepancies bounded below by -1. And then the only extra observation is that in the PLT case, so S plus delta is as before. So S is like the unique component with coefficient 1. Then in the PLT case, first of all, we have the discrepancy bound because we just proved that, but also we know that the restriction of delta, or is different because the restriction of delta Y to SY has coefficients strictly less than 1, because the delta piece is coefficient strictly less than 1. And so that's why we know it's actually KLT, not just PLT. Okay, so now you can see a strategy for applying inductive arguments. You have your DLT pair, you perturb, so you pick out a single S, you restrict, and now on that S you have a KLT pair of dimension n-1, and then you say, okay, let me assume that whatever I want about the minimum model program is true in dimension n-1, and try to use that to prove it for X. Of course, it's easier said than done. Okay, but now I wanted to at least state, though not prove, the hard theorem, which is usually what's called inversion of adjunction, which is the other direction for these statements. So let me just summarize it, and I'll say this is due in various forms to Shokurov, Kolar, and Kawakita. So I'm just going to summarize. There's a lot of statements that might be called inversion of adjunction. I'm just going to summarize one statement. So the inequalities above are actually equalities. And so the statements of the corollary are if and only ifs, with one caveat. Is that here, if we want to make them if and only if statements, we have to add the assumption that that xs plus delta is PLT in a neighborhood of s. Because of course, knowing something about s doesn't tell us anything about x completely away from s. So it's PLT in a neighborhood of s. So for the easy direction, we didn't need to assume that. It's okay to assume the stronger global condition, but if we want the converse, we better only be working on a neighborhood. Okay, so with that modification, then this hard inversion of adjunction theorem tells us that essentially these are if and only ifs. That if we want to, so this is quite useful because if you want to check that something is PLT or log canonical or something, what you can do is you say, well, let me take a generic hyperplane section, let that be S, slice by it, and check that when I slice by it, I get something that's KLT or log canonical. And then inversion of adjunction tells us that my original thing had these singularities in a neighborhood. So it's quite useful, but quite a bit harder than the easy direction. Okay, and the interesting thing is that actually this inversion of adjunction theorem has a direct proof, but also it's true that if you know the minimal model program, that will actually imply inversion of adjunction as well. So I think that's pretty interesting. But because the idea is you need to somehow control the discrepancies of these other divisors, right? Because not every divisor in a neighborhood of S, not every divisor of X whose center intersects S, so that lives in a neighborhood of S, is of the form the divisor you get when you start with a divisor on S, over S and then produce blowups to get a divisor sitting over it. Like in these inequalities for total discrepancies, right here, like the sets on this side are much bigger than the set of divisors that you produce of this form. And so you somehow need to control the divisors in a neighborhood of S to be able to prove these equalities. So that's why it's difficult. Okay, so that's enough of inversion of adjunction. Are there any questions? Okay, so in the last, well, maybe not the last, but the next kind of technical tool that's useful is this modified version of MMP called the MMP with scaling. So here's the basic idea. So we start with our pair x comma delta, so our KLT pair, and we suppose, well, actually that's not supposing anything. So we just have kx plus delta, and we let h be some ample. And let's suppose that kx plus delta plus h is at least nef. Of course, if we make h large enough, we can even suppose it's ample. Then what we can start doing is decreasing the coefficients on H. So now we consider, so maybe I can just draw a picture. Here's our cone. And then we have kx equals kx plus delta equals 0 line over there. We have our kx plus delta plus h line over here. And now we can start decreasing coefficients until we hit the effective cone. So basically we let T1 be the Neff threshold. It's the smallest, the smallest coefficient on H where the sum is still Neff. And when we do that, we're going to hit the boundary of the effective cone. So we're going to pick out some extremal rays. So my terrible picture, there's some extremal ray that we hit. But the point is that because H is ample, then actually this is an extremal ray, but it's a kx plus delta negative extremal ray because H dot R is greater than or equal to 0. So this is a as long as T1 is greater than or equal to 0. As long as T1 is strictly greater than 0. So if kx plus delta is already Neff, then we're done because we already have our minimal model. So there's no MMP to run. So basically we assume that kx plus delta is not Neff. Then we know that there's going to be some Neff threshold T1 that's strictly bigger than 0. When we hit that Neff threshold, we've picked out some extremal rays. Pick one of them, R. Now we have this extremal ray that's kx plus delta negative, but kx plus delta plus T1H 0. And so if we look at the extremal contraction for this ray, the observation is that Z, comma, the push forward of, well, let me just call it delta Z to just mean we've pushed forward delta plus T1 HZ, so we've pushed forward H as well. Then this is a weak log canonical model for the pair X delta plus T1H over B. So the observation is that while for kx plus delta, it's just the target of some extremal contraction. It's neither a minimal model nor a log canonical model a priori. Because we got it by adding this ample and kind of scaling down, then if we add that ample back into our divisor, then the log canonical is still Neff. So it's Neff on X, but it's also Neff on Z because we're contracting only kx plus delta plus T1H 0 curves. We're contracting curves where it's just trivial. So on Z, it's also Neff. And so we have a weak log canonical model for this pair delta plus T1H. And now we just want to, the idea is then to just continue. So if VR is small, we let X1 be the flip, if it exists. If VR is birational, is divisorial, then X1 is just Z. And if it's a Mori fiber space, well, then we're done. Then we've already that's the output of our minimal model program, and we're done. And now we repeat on this x1. So now on x1 we have a pair x1 delta 1 plus t1 h1, where this is some this is a weak log canonical model. So k x1 plus delta 1 plus t1 h1 is nef. And now we want to find some t2 smaller than t1, where now it hits the nef threshold. So where t2 so that for t2 minus epsilon, it's no longer nef. So we want to hit the boundary again. And now we want to say that when you hit the boundary again, you're picking out another extremal array. And then we can track that extremal array, and now we get the log canonical model. We get the log canonical model of delta 1 plus t2 h1 Okay, so where R1 is some extremal array that we've hit when we've reduced to our next nef threshold. The issue here is that H1 is no longer ample, because now H1 is just the strict transform of some ample on our new model. And so to actually carry this out, we need to slightly generalize to the case where H1 is not necessarily ample. All we know is that the sum is nef. And then there's the issue that if H1 isn't ample, we don't know for sure that when you hit the nef threshold, you're actually cutting out a kx plus delta negative extremal array. Because the way that we knew that up here was because h.r is strictly bigger than 0. So when we hit the nef threshold, kx plus delta has to be strictly less than 0, because we're assuming that the threshold is above 0. And so there's kind of a technical piece, which is that we need some bigness of delta to guarantee that R1 is a kx1 plus delta 1 negative extremal array. Okay. And I won't go through that argument, but that uses essentially these bounds on the cone the curves in the cone theorem, the bounds on their intersections that we didn't prove in the class. But once you have these bounds on the intersections, you assume delta 1 is ample. You write it is big, and so you write it as a nef plus as an effective plus an ample, and then you have to mess around with this and check that because there's only finitely many curves, because you have this ample piece in delta 1. And they have these bounded intersections, then you can let T2 be like the minimum of all the intersections with these finitely many negative extremal arrays, and check that that's actually the nef threshold, and therefore it does cut out an extremal array. Okay, so to run MMP with scaling, you need to assume bigness of delta, or maybe there's some other variance of the assumptions you can assume, but that's one assumption. And now you can keep going. Now you can say, okay, under this extra assumption, then I can find this T2 that cuts out an extremal array where I've hit the nef threshold. Now I can take an extremal contraction, a kx plus delta 1 extremal contraction for x1, which is also a kx plus delta 1 plus T2H1 trivial contraction when I add back the T2H1, and so I get that. So I get an x2. That's the log canonical model, or weak log canonical model of x1 with delta 1 plus T2H1 over B. And now we keep going. And the point is that at every step, if we at least assuming that flips exist, at every step, each extremal contraction and each step in the minimal model program actually produces a new weak log canonical model of our original pair with this coefficient. So the point is that in the end, this x2 is the weak law canonical model of x1, but x1 was this weak law canonical model of x, and so when we just decrease the coefficients further, this x2 is actually the weak law canonical model of our original x with coefficients delta plus t2h. And so in this way, what we get is a sequence like this, where at each step we have a law canonical model. So each step of the MMP occurs at coefficient ti, but and produces the weak law canonical, or a weak law canonical model of x delta plus TIH over B. And what this says is, if we want to show this terminates, we need to show that there are finitely many of these thresholds Ti. But that's equivalent to showing that there are finitely many weak law canonical models. And so termination of MMP with scaling, so that this is the important point, that termination of MMP with scaling is equivalent to finiteness of law canonical models for the pair x comma delta plus th as t varies. And so this is a strategy that that BCHM employ. One of the many things that they prove, which I'll summarize in a second. One of the many things they prove is finiteness of these models, and that's one of the steps in proving existence of minimal models. Okay. So the next and maybe last kind of technical ingredient is we still don't know that flips exist. So to do all this, we also need to guarantee that flips exist. And the observation of Shokarov is that it suffices to look at a restricted class called PL flips. So I want to define these. This PL stands for pre-limiting. It was introduced by Shokarov. So let x comma delta be a KLT pair. Or actually, no, let it be a PLT pair. And suppose that S is the round on of delta. And let's suppose that S is integral. So we know it's normal because the pair is PLT, and let's suppose we just have one component. So again, because these pre-limiting flips are flips that we can hope to understand by using induction and restricting to S. So that's exactly the point, that the strategy will always be use adjunction to restrict to S, and then use induction, assume that you know flips on S, assume that you know termination of MMP for S because it's one dimension lower, and try to get it for X. So PL flips are exactly the flips that are designed so that you can handle them with induction. So S is integral. Then we say that a PL flipping contraction is a kx plus delta flipping contraction. Well, let me call it phi, not f. So we're contracting a kx plus delta negative extremal array such that minus S is phi ample. So that's the extra condition. What does this tell us? Well, it tells us that whatever curves we're contracting, kind of the flipped curves, or the flipping curves for this phi, the curves in our array, they have to be contained in S. Because if minus S is phi ample, then S is negative on all these curves. And so the only way that's going to happen is if all these curves are contained in S. And so that's the key point, that in these PL flipping contractions, all the curves are contained in S. So if we restrict everything to S, then this contraction becomes some sort of extremal contraction of S with its different. That's the rough idea. So let's and then how do you prove anything? So let's suppose that Z is affine. Just to make things easier, because we already saw that the existence of a flip is the same as finite generation of some sheaf of algebras over Z. So let's assume Z is affine, so it's just an actual algebra. Then the existence of a flip was the same as finite generation of the ring of sections of Kx plus delta. And so now we write delta as S plus B, where B is the fractional part of delta. And we look at our exact sequence of sections. By adjunction, this restricts to S, M, Ks plus the different. And so we get a restriction map on algebras as well, because these are the algebras of sections. So we get a restriction map from the log canonical ring of Kx plus delta to the log canonical ring of Ks plus the different. It suffices to prove that the image, so this is an observation of Shokarov. Is finally generated. Now, if we're in the very nice case where the restriction is surjective, then we can induct on dimensions. So we can say, okay, suppose we know all the conjectures of the minimum model program in dimension n-1, then we know that Rs Ks plus the different is finally generated. Then we have this surjection, and then you use your exact sequences to prove that Rx comma Kx plus delta is also finally generated. But this map isn't going to be injective in general, because B can be, anything. It's just the rest of the boundary. So it's not going to be surjective in general. And so Shokarov pointed out that we just need to prove that this restriction is finally generated. The image of this restriction, and he called this the restriction algebra. So using this inductive idea that for these prelimiting flips, kind of all the action is happening inside of S, then Haken and McKernan showed that MMP in dimension n-1 actually implies existence of PL flips. And in this field, people like to just index the names of the statements with the dimension. So you might write this as MMP n-1 implies maybe PL flips in dimension n. And the way they did this was, a very, very, very rough idea. So again, you want to be able to say that this restriction map is surjective. And then if you assume MMP in dimension n-1, then you know that the log canonical ring is finitely generated, because you've assumed all the conjectures, and so then you know that Rx Kx plus delta is finally generated, and so then you have PL flips. You don't know this thing is surjective, so you have to take some log resolution and run some MMP, or yeah, basically take some birational transformations that produce a new model where now you have a T dominating this S, where if you pull everything back to this T, then this restriction map becomes surjective. That's essentially the idea. And then I mean, it's a lot more complicated than that, but they basically produce this birational model where you do have the surjectivity, and then you have finite generation by assumption, and then you lift it to finite generation by the ideas of Shokarov. And then the reason that Shokarov introduced these PL flips was that he actually showed that essentially all you need are PL flips to get all flips. So he showed that MMP in dimension n-1 plus PL flips in dimension n implies all flips. Or colloquially referred to as BCHM, which are the 4 authors. Okay, so here's the most important theorem. So let's say we have f from x comma delta to b is a q factorial KLT pair that's projective over b. And suppose that delta is big over b, then any MMP with scaling terminates. Okay, so amazing theorem. We still don't know that that arbitrary MMPs terminate, but essentially this is all you need for the most important applications. By the way, my numbering is not the numbering from their paper. I'm just writing it in order that I'm presenting. So in the same situation, but suppose either delta is big and kx plus delta is pseudo-effective, or kx plus delta is big. So this is why, I mean, this is the case in the title of the paper for varieties of log general type. Then we get a bunch of corollaries of theorem 1. 1, x comma delta has a log terminal model or a log minimal model, and in fact it's good. 2, if kx plus delta is big, so here I should have put f everywhere because this is all relative, then x comma delta has a log canonical model. 3, the ring of sections is finitely generated. Okay, so let me say a few words about how theorem 2 essentially directly follows from theorem 1. And maybe I'll stop there for today. So the issue, we want to apply theorem 1 directly, but we have these two possible assumptions. So if delta is big, then we just apply theorem 1 and we know that we can run MMP with scaling. But the other possibility is that we don't assume anything on delta, but we have that kx plus delta is big. So we're in the log general type case. So first, let's see why we can still apply theorem 1 in that case. So if kx plus delta is f big, then we can write it as some d, which is effective because it's big, so it has a lot of sections. So there's some Q divisor d that's effective, that's equivalent to kx plus delta. And so now we can consider delta prime to be delta plus epsilon d. Now this is big because it's divisor of the form big plus effective. The pair x comma delta prime is KLT because we've added some epsilon multiple of an effective, and that preserves being KLT. But on the other hand, kx plus delta prime is numerically equivalent to kx plus delta times 1 plus epsilon, right? Because d itself is just equivalent to kx plus delta, and then we're adding epsilon d. And so the kx plus delta minimum model program is equivalent to the kx plus delta prime minimum model program because the intersections are just the same. So sorry, kx plus delta prime. But now with the pair x comma delta prime, we have the assumption that delta prime is big. So by theorem 1, MMP with scaling terminates. But now once we know that MMP with scaling terminates, then we know that we have, well, we have a diagram. So in either of these cases, we've assumed that kx plus delta is pseudo-effective, because if it's big, it's pseudo-effective, or in the other case, if just delta is big, then we added the assumption that kx plus delta is pseudo-effective. So in either case, we can't end up with a Mori fiber space, because for a Mori fiber space, there are no sections. So once we know that MMP with scaling terminates, then we know that it has to terminate to a log terminal model. So now we have a log terminal model. That's part 1. Part 2 is just the base point free theorem, because in the case that kx plus delta is f big, then we can apply the base point free theorem to our log terminal model, because now our log canonical divisor is big in f. And so we have a base point free linear series, and its image is exactly proj of the log canonical ring, and it's a log canonical model. Everything's finally generated, and we have existence of log canonical models. For 3, basically they show that but for 3, basically you want to show that the base point free theorem applies in the case where you just assume that delta is big, where you don't assume that kx plus delta is big, but you just assume that delta is big. So 2 plus 3 in the case kx plus delta is big is just the base point free theorem, and 3 in the case delta is big. Basically, they show that you can write down kx plus delta is equivalent to kx plus a plus b, where a is ample and b is an effective, such that x comma b is KLT. So of course, you can write down delta as ample plus effective, and so you'll say, okay, let me just write that. But if you just do it without checking anything, then there's no reason that x comma b is KLT, because if you just write down delta as an ample plus some arbitrary effective, the singularities could be bad, the coefficients could be large, who knows? So they have to give some arguments to show that you can do it in such a way that x comma b is KLT, but now kx plus delta minus kx plus b is ample. It's A, but it's also ample. And so if we let this be D in the BPF theorem, then that implies base point freeness, which implies that models are good and implies finite generation.